So just based on what we learned in the last lecture, we will do a bit of practice questions. Then we will get back to first law of thermodynamics. So anyhow, let's begin. Okay. So what we were discussing in the previous lecture was about the relationship between potential energy and the internal conservative force in a one-dimensional system. So we had seen that delta U is minus f dx integration, where f is nothing but the internal conservative force, and similarly f is minus du by dx. That is, the internal conservative force is negative gradient of potential energy. And from this, what we had understood is that du by dx equals to 0 means that f is 0, which becomes an equilibrium position for a system with net force equal to this internal conservative force. That basically means that for that system, external force should be 0 and non-conservative force should also be 0. Then for such a system, it becomes an equilibrium position. And further, if it is a position where potential energy has a local maxima, then it is an unstable equilibrium. And if it is a system where potential energy has a local minima, then it is a stable equilibrium. Okay. So let's quickly do an example before we move ahead of this concept. So now let's say we have a 1D system along the x-axis. Yeah, doubts we'll do in next week. One of the lectures we'll do. Okay. So you have time till next week to go through the question set from the module, etc. Okay. We're just doing some additional practice problems today. Yeah. So 1D system along the x-axis with a particle of mass 1 kg under the action of only a single conservative force. Okay. Such that its potential energy is now given by this function. It is x cube minus, let's say, 18x, where x is in meters and potential energy is in joules. So first of all, find the position or positions of local maxima, minima. Okay. And secondly, if the particle has a speed of plus 2 I cap, a velocity of plus 2 I cap at x equal to 0, then find its maximum kinetic energy, maximum potential energy, and maximum displacement along the positive x direction. Okay. So these are the various things we have to calculate. Just try out this question. Prince, check your solution again. You are telling position of local maxima or minima. Okay. And what about maxima? Okay. But the value is not correct, but one small mistake. The number of points is okay, but just that value you got for x, na? Just check that once more. Yes, Santrish, that's correct. Very good. So basically, see, we have to find for the first partner, we have to find the position of local maxima and minima.
Root 6.
Yes, that's correct. Of potential energy. That's correct. Root 6 is maxima or minima?
Root 6 is minima and minus root 6 maxima.
Root 6 will be local maxima. Sorry, local minimum. And minus root 6 will be maxima. That's
Yeah.
correct. Very good. Okay, so in case you have not worked this out, anybody, just pay attention here. So, how will you find maxima minima? So, given the function, first step is find du by dx. So, that is 3x square minus 18. Then find second derivative. So, that's derivative of this. So, that is 6x. Okay. Then find the turning points. Turning points are points where there is both maxima or minima. So, turning points are positions where the rate of change is 0. So 3x square minus 18 is 0. So that is 3 into x square minus 6 is equal to 0. So factorize that and you get this. So we get two turning points. X is equal to root 6 and x equal to minus root 6. So you can say plus minus root 6. These are my turning points. Now to understand which turning point is giving you local maxima and which one local minima, you have to do what is called the second derivative test. So having got the turning points, next you have to do second derivative test. The test is that d2u by dx square is positive, implies that there is a local minima, and negative implies that there's a local maximum. So from this you can see that at x equal to root 6, the second derivative's value is equal to how much? 6 root 6. It's positive. Okay. So that means at x equal to root 6, U has potential energy has a local minimum, and the value of that local minimum is equal to root 6 cube minus 18 into root 6. So 6 root 6 minus 18 root 6. So minus 12
Well,
root 6 joules. This is the local minima of the potential energy, and it occurs at the point x equal to root 6. And likewise, if you look at the other point at x equal to minus root 6, the second derivative is minus 6 root 6. So it is negative. So that means there is a local maxima at x equal to minus root 6. And that local maxima has a value of u at x equal to minus root 6. So that is minus root 6 cube minus 18 times minus root 6. So this will become minus 6 root 6 plus 18 root 6. So its value is plus 12 root 6. So this is the value of the local maximum. In general you can do that, but in certain cases, if there are a lot of maximas minimas, it can be a little tricky. In this question, there's no problem because there's one local maxima and one local minima. But I'm just saying hypothetically, if you have a function which has a lot of peaks and dips, you can have a situation like this now. Now you can see that at this point, the value is more than the value at this point, but there is still a value of local maxima and there's still a value of local minima. So it's a very complex function having that property, which will generally not occur in physics, but that is why we have the second derivative test. Okay. Okay, so I'll just take you through this once more. So now we have not only the positions where there is local maxima and minima, but we even have the values of local maxima and minima. So that's going to be important for us. Okay. So root 6 is something close to 2.45. And 12 root 6 is about 29.4.
Sir, can you send the notes of last lecture in group?
Yeah, I have actually just now. Okay. Few minutes back, I've sent it. I've sent the notes of the lecture on 18th March as well as the one on 13th March before that. So I think even that was pending. Saw it now?
Yes, sir, got it.
I will send the videos also, but for now, just now, I just sent the notes. Okay, so people, this is clear, na? Local maximum, minimum.
Sir,
Yeah, yeah, tell me
sir,
what.
it is necessary to find the value of u minimum and maximum after local minimum and maxima.
No, in the question it had asked only the position, but the second part of the question, where we are finding maximum kinetic energy, minimum potential energy, all those things, there it will become necessary.
Yes, sir, got it.
Understand me? So I'm just doing it as an extra part. Okay. So in conclusion, what we are getting is that at x equal to root 6, which is approximately 2.45, the potential energy has a local minima, okay, which is minus 12 root 6, which was approximately minus 29.4 joules. Okay. Whereas at x equal to minus root 6 meters, the potential energy has a local maxima of plus 12 root 6 or approximately plus 29.4 joules. So these two things I'm going to make use of.
Sir, can you show the question second part?
The question now. Okay. Okay, so now second part. If the particle has a velocity of 2 I cap in meters per second at x equal to 0, then we have to find the maximum kinetic energy it will have, the maximum potential energy it will have at any stage, and also the maximum displacement. Yeah, I'm showing the answer again. Just a minute. So this is the first part's answer. Okay, now let's come to the second part. Now, when you're doing the second part, it's also useful to understand what the force would be like. So that is minus du by dx. So it is minus of the gradient of x cube minus 27x. Okay. So it's basically, sorry, not 27, 18. So this will become 18 minus 3x square. Okay. So we can also see that when we release the particle, or you can say when we project the particle at the origin, okay, x equal to 0, okay, we projected the particle with an initial speed of 2 meters per second. But we can also understand the force acting on it at x equal to 0. The force on the particle is plus 80. So obviously it has an acceleration in this direction. So it will increase in speed. Okay. But what you can also see is that at x equal to, now how much? Root 6, the force will become 0. Okay. Because this is a stable, or rather, this was an unstable equilibrium position. Okay. So that is one thing we have to just add to the answer of the previous question, that we have to understand that the position of local minima, this is the stable equilibrium. So x equal to root 6 has the stable equilibrium point. Okay. And this position of the local maxima has the unstable. So x equal to minus root 6 is the unstable equilibrium point, which I've just understood from the concept of local maxima and minima so far. Okay. We can later also plot the graph and understand this better. But yeah, so at root 6 there is a stable equilibrium position. So the force will be 0. But at x greater than root 6, what is happening? The force will become negative. Okay. So what is happening is that from here, as it is starting, let's say it goes to x equal to 1, x equal to 2, and like that. By the time it comes to x equal to 6, now at x equal to root 6. So root 6 is just beyond 2, so somewhere here. So at this point of time, just for an instant, its acceleration becomes 0. But up till this point, the acceleration is positive. Okay, because okay, but the moment it crosses this point now, where x becomes greater than root 6, so x is equal to 3, x is equal to 4, but in general, greater than root 6. At that position, what is happening? The force is negative, so the body starts to decelerate, like we'd seen in the last. Okay. So we can see that stable equilibrium is where potential energy has minima. So obviously kinetic energy has maximum. Okay. Or you can see from x equal to 0 to root 6, it accelerates. And root 6 onwards, okay, it decelerates. So obviously it makes sense that therefore V is maximum. So kinetic energy is maximum at x equal to root 6. So that is what will help us understand the maximum kinetic energy. So by the time it reaches here, whatever its speed is, this will be maximum. Because after that it starts decelerating. So for this part, we'll now use work energy. So we can see that therefore, conservation of energy that change in kinetic energy plus change in potential energy is zero. Okay. And at x equal to root 6, we have potential energy is local minima, which we had seen was minus 29.4 joules or minus 12 root 6 joules. And kinetic energy is maxima, if you want to calculate. So from x equal to 0, where the kinetic energy is half mu square, where u is 2 meters per second, and the potential energy is equal to 0 joules. Because you can see that the formula for potential energy was such that, so you can see that potential energy at x equal to 0 is 0. Okay. So from x equal to 0, where this is happening, to x equal to root 6, the change in kinetic energy plus change in potential energy should be 0. So half mv is maximum value square minus half mu square plus potential energy at root 6 minus potential energy at 0 should be 0. So half into whatever mass we have taken, 1 kg. So half into 1 into V max square minus half into 1 into 2 square plus this one, which is minus 29.4. This should be 0. So V max square by 2 is equal to, this will become 2, and on that side this will become 29.4. So 31.4 joules. So this is your maximum kinetic energy. Maximum kinetic energy, that will be 31.4 joules. In fact, we don't need to substitute the value of mass because we are just interested in calculating the maximum kinetic energy. You can just keep this as, okay. In this we are substituting so that we get, so this is identical to the question we have done in the previous lecture, but that there the potential energy function was a parabolic function or a quadratic function. Here I have given you an example of a cubic function. So it's a little bit more involved mathematically, but it's exactly the same steps. Okay, so just try this out. So second part of the question, what is given to us is that its initial velocity is plus 2 I cap at the position x equal to 0. So from this we have to find the maximum kinetic energy, maximum potential energy, and maximum displacement along the positive x direction, these three things. So I've just found you the maximum kinetic energy. Okay, so this is clear, I hope. Now next you can see that,
Sir,
yeah,
sir, while using potential energy in formula of mechanics, why we took the root 6 to 0?
by using the potential energy we put,
Sir, in this formula, kinetic
huh,
energy and change in potential is 0.
yeah,
We
U
took,
is zero. This na potential energy at zero is zero. You're saying how we got that?
no, sir.
Then,
Why we took root 6?
because that is where the potential energy is minimum ना, तो वहीं पे kinetic energy maximum होगा. Okay.
Okay, sir. Yes,
So
sir.
this point over here that we know that at x equal to root 6, the potential energy is minimum. So at that point only kinetic energy must be maximum. So how much is that kinetic energy? Yeah. So in
Got it, sir.
general, the sum of kinetic energy plus potential energy is constant. Okay. So now for this thing we know that if potential energy is minimum at some point, that means kinetic energy is maximum at that same point. So this is occurring at which point? It's occurring at the stable equilibrium position.
Got it, sir.
Okay. Okay. So now next thing we want to find that the potential energy is maximum. I mean, what is the maximum potential energy is value we have to find out. Okay. So potential energy is maxima we have to find out for the same situation. So once again, kinetic energy plus potential energy is constant, and that is the value of E at x equal to 0. For example, we know the kinetic energy is half mu square, which was coming out to be 2 joules, and the potential energy was coming out to be 0. So the total mechanical energy was equal to 2 joules. Okay. So now at a certain value of x, kinetic energy becomes 0, which is the minimum value of kinetic energy. So correspondingly, potential energy becomes maximum. Okay. So, so this one's minimum value is equal to 0. So this one's maximum value we want to find out. So that is equal to 2 joules. So obviously you can see that U max is equal to 2 joules. The potential energy cannot be more than 2 joules because the total mechanical energy is only 2 joules, and kinetic energy cannot become a negative quantity. No? Kinetic energy is a non-negative quantity. So minimum value of kinetic energy possible is 0. So it's only when the particle stops at whatever position, at that position the potential energy should be maximum, and that value of maximum potential energy will be 2 joules. Okay. And also U will be equal to U max at the maxima or the maximum x coordinate. The particle will not go beyond that position because the potential energy cannot increase further. So we'll put the potential energy function, which is this one, x cube minus 18x. Now when we put that equal to 2, whatever value of x that we will get, that corresponds to maximum value of x. Okay, so now that is not something that easy to estimate because it's a cubic function. But you can see, for example, potential energy's value at x equal to 4 is how much? Still a negative quantity only.
Sir, we can take one x common.
Minus 8. We can do that. Potential energy at x equal to 5 is 5 cube minus 18 into 5. So 25 minus 18. So it's plus 35. So between 4 and 5, it's doing a massive jump. It's doing a massive jump from minus 8 to 35 between 4 and 5. So there must be some value in between where it's plus 2. Okay.
Sir, 3 root 2.
3 root 2. How you got the value 3 root 2?
Sir, x cube minus 18x, so x will take common. Then x square minus 18 is equal to 0.
Is equal to 2. Right?
Oh, sorry, sir.
So it's not that simple, but I'll just tell you. Okay. So for example, if I were to take 4.5 and do this calculation, so 4.5 cube would have given us 91.125 and minus 18 into 4.5.
Sir, 2 root 5.
So this would give us, so u at 4.5. I'm doing the calculation and it comes out to be somewhere around 10.12. So it's even less than that. So let's take 4.
Sir,
Still
2
we are
root 5 is coming 4.47.
4.47, 2 root 5. Okay. So, that's some kind of value in between. Like, so more important for us here is to understand that, the graph of potential energy versus X is going to be this sort of graph. Local maxima, then local minima, then again it starts increasing. So this point is root 6. This point is minus root 6. This minimum value of potential energy is uh, minus 29.4 joules, and this maxima here is local maxima is plus 29.4. So now what is happening is that when we start off now, our kinetic energy is some positive value, 4 joules or 2 joules or whatever like this. So initially our potential energy is decreasing, so our kinetic energy will increase. It reaches the maxima. So this is now our kinetic energy at root 6. But then our potential energy starts increasing. So our kinetic energy also starts decreasing. And at some stage, the kinetic energy becomes 0. So at that stage, the potential energy's value must be 2. So where the kinetic energy becomes 0, at that point, the potential energy's value must be equal to 2 joules because the total mechanical energy was 2 joules. So this is how the kinetic versus potential energy graphs look. So if we just keep doing a bit of experimentation with these values, we'll come to something close because there's no direct formula for it. Let's try 4.2. So 4.2 cube will give us 74.1 minus 4.2 into 18,
Sir,
which is,
minus 1.5.
so this is giving us minus 1.51. So now it's in between these two. So it's probably somewhere around 4.3 or 4.4, somewhere in that region.
Yes, sir, coming in between of 4.2 and 4.3.
Yeah. But anyway, understood the concept of stable and unstable equilibrium na, in this question.
Sir, to find the maximum potential energy, we did this, na?
Yeah, मैक्सिमम पोटेंशियल एनर्जी के लिए सिर्फ काइनेटिक एनर्जी को जीरो पुट करना था, सो वो तो आ गया 2 जूल्स. बट पोजीशन एट विच मैक्सिमम पोटेंशियल एनर्जी occurs or the maximum displacement, for that we have to put the value of potential energy equal to 2 joules and solve this equation, which is not something very trivial because cubic equation in maths is more complex compared to quadratic equation and all. There's no direct formula, so what we are estimating from our analysis is somewhere in between. X maximum will be greater than 4.2 but will be less than 4.3 probably. It will be some value in between these two, where the potential energy reaches the value of 2 joules. That means the particle stops because the kinetic energy becomes zero. Right, so this is clear?
Yes, sir.
Okay. Now moving on to the last part conceptually of this discussion, uh, we'll come to a more general case when there is three-dimensional motion.
Sir, what you told about the displacement of that question?
Maximum displacement ना, maximum x coordinate कहाँ पे होगा? जहाँ particle stop करता है for a moment. So where the particle stops, okay. Why is this the x maximum? Because at x equal to x maximum only, my potential energy is becoming 2 joules, which is the maximum of potential energy, and kinetic energy is becoming zero. So the particle is stopping. So it doesn't go beyond that position. So that thing, whatever the value is between 4.2 and 4.3, the particle goes up to that point, but does not go beyond because it decelerates and comes to rest at that point.
So displacement also must be between 4.2 and 4.3.
So maximum displacement का value ही होगा something between 4.2 and 4.3.
Okay, sir.
Okay. Okay, now what we had learned about this thing, the relationship between potential energy and internal conservative force for one-dimensional situation. Now we will look at a general situation, general three-dimensional system. Okay, and the relation of potential energy with respect to the internal conservative force. Okay. So this is a little bit advanced in terms of concept, and you have to keep in mind that what we are discussing here, it is more for application in future chapters like electrostatics, and it is more for application in JEE advanced level questions. This is not for JEE mains level. Okay, because we will be learning a new operator in mathematics called the gradient operator from this. So what happens is that in a 3D system, if my internal conservative force is having all three components, Fx, Fy, and Fz, okay. And we know that change in potential energy is defined as negative of work done by the internal conservative force or minus of integration of F internal conservative dot ds. So you can also say that in a small displacement, the change in potential energy du is minus F ds, where F is this internal conservative force. So this equation now, it results in this. I'll be substituting this value of force with all three components. And because it's a 3D system, my displacement ds will also have three components, dx, dy, and dz, because it's a three-dimensional system. So my particle or body or whatever could be moving with all three components or any combination of concepts. So this will also be substituted here. So on substituting the value of force in this, what we get, our change in potential energy du for this small displacement becomes minus of fx into dx plus fy into dy plus fz into dz. So it becomes like a three-dimensional version of what we had seen for 1D system. There it was minus f dx, here it is minus fx dx minus fy dy minus fz dz. So this becomes this relation. Now, how can we basically invert this to get force in terms of potential energy? So first of all, this is showing us that potential energy is a function of all three variables. Okay, so that is where the maths becomes a little bit more complex, because now our potential energy is a function of three variables. It's a multivariable function: x, y, and z. Now, this is something that we haven't learned in calculus or math so far, because so far in calculus, what we've learned is a function of x. I mean, it's a single variable function. This is an example of a single variable function. But now we are learning a case where the function will become of three variables, x, y, and z. So accordingly, for such function, we have slightly different principles of defining this. Okay. So from this equation, du is equal to minus of fx dx plus fy dy plus fz dz. What we can observe is that if dy is 0 and dz is 0, which basically means that y and z are kept constant, okay, then we can say du is equal to minus fx dx under the condition that dy is 0 and dz is 0. So in that case, I can say that fx is minus du by dx. But considering that, keeping y and z constant, because I want dy and dz to be 0. So that condition is in maths, it is given a new operation. It is called partial differentiation. Partial differentiation with respect to x. And it is written with the symbol dou by dou x. Instead of d by dx, this symbol is called del or dou. Okay. So this can be read as del by del x or dou by dou x, and it is read as partial differentiation with respect to x. Okay. So this gives us that x component of f becomes negative of partial differentiation of u with respect to x. This statement that it is partial differentiation, this itself implies that it is minus du by dx under the condition that all other variables like y and z are constant. They are to be treated like constants. So I'm differentiating u with respect to x, keeping y and z like constant. So in that case, the rate of change that I get, that is called the partial derivative or the partial differentiation. So the x component of force becomes negative of the partial differentiation of u with respect to x. Similarly, we'll see y component will become negative of del u by del y, and z component will become negative of del u by del z. So we'll get three different formulae in terms of the three different partial derivatives for the individual components of f, which are fx, fy, and fz. That's why
Uh,
I told you that the mathematics is a little bit more complicated here. Yeah,
so except the differentiation, other two are constant, na sir?
yes, yes. That we'll understand with some examples how to do the partial differentiation. Okay. Right now, we just write down the definition of what is partial differentiation. It is differentiation of the function u with respect to x, while y and z is constant. Okay, so we will look at the execution of this operation with some examples. So don't worry about that. Just write down this definition or make sure you understand this definition as of now. Okay. Now, very similar to this, what we can do is for potential energy relation with Fy and Fz. So similarly, we can see that for dx equal to 0 and dz equal to 0, that means x and z being constant, the relation becomes du is equal to minus f by dy for x and z being constant. So the inverse of this relation is that Fy is negative of partial gradient of u with respect to y. And likewise, Fz will become negative of partial gradient of u with respect to z.
Sir, so is partial difference same as differentiation normal?
Yeah, it's similar to normal differentiation, but only thing is we have to do the differentiation of a multiple variable function, keeping the other variables constant. So I'll explain with examples and it will become clear. So here in general, what we'll say is that if potential energy is a function of all three coordinates x, y, z, that means my internal conservative force will have all three components fx I cap plus fy j cap plus fz k cap and each of those components will be given by the corresponding partial gradient, but with a negative sign. Okay. So this is the final result that you have to keep in mind. Okay, so let's understand this with an example. So first of all, let's look at partial differentiation. So it applies to functions of multiple variables. For example, suppose we have a function that theta is equal to x square plus 2xy. So we can see that theta is a function of x and y. Okay. So then d theta by dx does not exist. Okay. Or d theta by dy does not exist. It cannot be defined for this function because theta is a function of two variables, x and y. Okay. So these are in fact in mathematical language now, these are called perfect derivative. This is perfect derivative with respect to x. And this one is perfect derivative with respect to y. Okay. But instead, del theta by del x, that is basically applying the differentiation to this function. Okay. This is partial derivative. Okay, which means that we are differentiating with respect to x while y is constant. Okay. So partial derivative with respect to x means that we are differentiating with respect to x, but any other variable that is there in the function, it is treated like a constant. So if you were to treat y like a constant here, you can see this derivative would become 2x plus 2y or 2 times x plus y. And similarly, partial derivative with respect to y would become differentiate this with respect to y, but as if x is a constant. So differentiation of constant with respect to y would give us 0, and differentiation of 2xy with respect to y would give us 2x. So this would become 2x. Okay. So this function now is such that it has partial derivatives. Instead of perfect derivatives, it has partial derivatives. So partial derivative with respect to x is 2 times x plus y. Partial derivative with respect to y happens to be just 2x. That is the nature of the function. Okay, so hope this is clear how we have done the partial differentiation process here. Just note down this example, then we'll come back to potential energy and force.
Sir, can you explain it again?
Yes, Beta, what was the question?
Can you explain this again, last part?
So see, when I'm writing the operation del theta by del x, na, that means I'm doing partial differentiation or I'm finding the partial derivative of the function with respect to x. That means उसमें मुझे क्या करना है? I have to differentiate the given function with respect to x as if any other variable in the function which is present is a constant. So in this case, there is only one more variable which is present, which is y. But I have to differentiate with respect to x as if y is a constant. Understood, man? This first thing that we're doing, del by del x, we are differentiating this with respect to x, but as if y is a constant. So differentiation of x square with respect to x is 2x. Differentiation of 2xy as if y is a constant is nothing but 2y. No? So is this clear, beta? Now similarly, when we differentiate with respect to y, partial differentiation with respect to y. So what we're doing, we're differentiating the whole function with respect to y, treating x like a constant. So differentiation of a constant is 0. Differentiation of 2x into y. So x is a constant. So it is just some constant into y. So its derivative is 2x. So now x is the constant and y is the variable because we are doing partial derivative with respect to y. So the function has two variables x and y. So accordingly the function has two partial derivatives. Del theta by del x and del theta by del y.
Sir,
Yes.
sir, how it came 2y in place of 2xy?
हाँ because देखो ना मैं ये कर रहा हूँ ना partial derivative of 2xy with respect to x. So in this y is a constant. Na? So you will take 2y constant outside and differentiation of x with respect to x is 1. Na?
Yes, sir, got it.
Or like that. Now similarly in the second one, the derivative with respect to y of x square is what? 0 because x square is a constant. But the derivative of 2xy with respect to y now. So this time we will take 2x outside and differentiate with respect to y itself. So that is 1. That is 2x into 1. That's 2x. That's how we got this.
Got it, sir.
Okay, good. This is the partial derivative with respect to y. That is differentiate with respect to y, treating x like a constant.
Done, sir.
Yeah, done now. So partial differentiation, and just to answer your question, it applies when we have a function of multiple variables. And perfect differentiation is only applicable when we have a function of single variable. We cannot do perfect differentiation of a multiple variable function. Okay. So now let's look at an example of this in
Sir, but how exactly we can know that we have to use the partial differentiation or normal differentiation?
वही बात है ना. See, suppose our function is given as u is equal to, let's say, 3x square minus 2x. So what we observe here, that u is a function of x alone. Okay, so that means the force will have only x component, and that x component will be minus du by dx, because u is a single variable function. Okay, but if I have an example where u is a multiple variable function, like let's say it is x square y plus y square z plus zx. Okay, where u is energy in joules and x, y, z are coordinates in meters. Now I ask you, what about the force, the internal conservative force? So immediately you can see that the potential energy is a three variable function. You can observe here that the potential energy is a function of x, y, and z. So therefore, du by dx does not make sense. Instead, del u by del x makes sense, del u by del y makes sense, and del u by del z makes sense. So that shows us that the force has three components: fx I cap plus fy j cap plus fz k cap, and such that each component is negative of gradient with respect to that particular coordinate. Understood the difference between these two?
Yes, sir.
Okay, now let's just do this calculation. So if I differentiate this function with respect to x, treating y and z like constant, how much will it be? See, x square y का differentiation क्या हो जाएगा? Y is a
2,
constant,
2x.
2xy. Now y is also there, na, because it's a constant. Then y square z, it's just a constant, so its derivative is 0. Okay, and then z into x. So you are treating z like a constant into x. So this will be z. Okay. Similarly, partial derivative, of course, with the minus sign, because the force is negative gradient of potential energy or negative of partial differentiation. So minus sign will be there. Okay. In the second term, now differentiate this with respect to y as if x and z are constants. So the first term will give us x square. The second term will give us 2yz. The third term will give us 0. And similarly, the z component of force will be minus del u by del z, and that will be minus of, the first term will now give us 0, the second term will give us y square, and third term will give us just x. So these are the individual three components of force. So therefore, I can say that the force is like this. It is minus of 2xy plus z I cap plus x square plus 2yz j cap plus y square plus x k cap. These are the three components of the force. This kind of an internal conservative force produces this type of a potential energy. So they are linked to each other in this way. This formula of potential energy corresponds to this value of internal conservative force. So hope this is clear now.
Yes, sir.
Okay, very good. So just make a quick note of these two examples, then we will solve another question based on this. Now, typically these type of three-dimensional examples and all will come in later chapters like gravitation, electrostatics, etc. So you will not find too many questions of this type even in your module, and none of them are there in HC Verma. HC Verma has only questions the type we've discussed earlier, application of work energy theorem, things like that. But nonetheless, this is going to be very useful for our further chapters in physics also, and plus for JEE advanced level questions.
Ram.
Done. Sir.
Okay. So let's look at a quick example now. So a particle of mass 2 kg moves under the action of a single conservative force F in a two-dimensional plane, okay, which is the xy plane, such that its potential energy is given by this function. It is 20 divided by square root of x square plus y square, where the coordinates xy are in meters and u is in joules. So first of all, find its acceleration at the position 3 comma 4 in meters. Okay. And secondly, if it is released from rest at x equal to or from the position 1 comma 0 in meters, okay, then which direction will it move in? And find its speed after a distance of 3 meters. After traveling a distance of 3 meters. Okay. So just try out this question, people. Okay, so people, anybody got the answer? Okay, Kshitij, let me check the answer for you. So what we have to do is now from this potential energy function, first of all, we have to find the internal conservative force, this force F, how much that is. Okay, so you can see that potential energy is a function of x and y. So that means that the force has two components, Fxi cap plus Fyj cap, where Fx is minus del u by del x and Fy is minus del u by del y. So this is what we have to do. Okay, now potential energy is 2 upon, or rather 20 upon square root of x square plus y square. So this will become negative of partial differentiation of this. So 20 comes outside. Now differentiation of 1 upon root of x square plus y square. So that is minus half into x square plus y square to the power minus 3 by 2. Okay, into the differentiation of this term with respect to x, treating y like a constant, so that's 2x. So this, as you can see, will become 20x upon x square plus y square to the power 3 by 2. This is what our x component of force will become, Fx. So make sure these steps are clear to you. I'll just show you on the side how we are doing the differentiation. Okay. Differentiation of, for example, 1 upon square root of some constant a square plus x square. How we do this? This is equal to differentiation of x square plus a square to the power minus half. So we apply the chain rule. Okay, so we treat this whole thing like z. So z to the power minus half. So it is, its differentiation is minus half into z, which is x square plus a square to the power minus half minus 1 into differentiation of z with respect to x. So that is nothing but differentiation of x square plus a square. So that's how this becomes. Okay. So this is the differentiation of this term. This is this. Okay. Now just like we have done this, same way over here, but instead of a we have y. It makes no difference because we are treating y like a constant, just like we treated a over here as a constant. So here a is a constant. It could be some number like 1, 2, 3, 4, etc. So this is the chain rule method of differentiation that we're using. Now, just like we've done this to find out fx, now you do the partial differentiation of u with respect to y and put the minus sign to get the y component of force. And you'll see that's symmetrical. So you'll get the formula for force as a two-dimensional vector as a function of x and y. And then you just calculate the net force at the given point, which is 3, 4. So net force divided by mass will give us the acceleration. Yeah, so Ansh, I'll explain this again. This is an application of differentiation by chain rule. You have heard of this, na? Differentiation by chain rule. Composite functions and chain rule. Yes, so that is the thing we're doing. Okay, so for example, okay, I know that differentiation of sin x is cos x. Okay, but if I have y is equal to sine of 3x, then how will I find out dy by dx? So I'll have to use chain rule. So what I'll do is I'll substitute 3x as some new variable. Okay. So accordingly, y will become sine z. And then I'll use the chain rule step that dy by dx is dy by dz into dz by dx. So that becomes differentiation of sine z into differentiation with respect to x of 3x. Okay, so that becomes cos z into 3. So that finally becomes 3 cos 3x. Okay, so this kind of principle. No, we cannot do like that. No? We cannot. We have to differentiate with respect to x, not with respect to 3x. So like that. Okay. So this example you have understood, Ansh. This example is clear. Okay. So now similarly we have to use this thing that if I have y is equal to, let's say, 1 upon square root of x square plus 4, I suppose very first one. So that is 1 upon square root of x square plus 2 square, like that. Okay. So I want to find dy by dx. So what I'll do is first step I'll do substitution. So substitution में क्या करूँगा? I'll substitute x square plus 4 as z. So y becomes 1 by root z, or z to the power minus half. Then second step I'll use the chain rule that dy by dx is equal to dy by dz into dz by dx. So that is differentiation of z to the power minus half into differentiation with respect to x of z, which is x square plus 4. Now understood where the 2x is coming from. So this is minus half z to the power minus half minus 1 into this term is becoming 2x. So this is minus 1 by 2 z to the power 3 by 2 into 2x. So that becomes x upon z to the power 3 by 2. So that becomes x upon x square plus 4 to the power 3 by 2. So this is something very critical that you should know how to do. In number of places, this chain rule kind of application is there in physics, and you should have no confusion in how to apply chain rule. Okay, very good. Okay. So now coming back to that question, potential energy was 20 upon x square plus y square square root. So fx we already saw, minus del u by del x. This we had got. It was 20x upon x square plus y square to the power 3 by 2. Now fy, similarly if we calculate, we will get as 20y divided by x square plus y square to the power 3 by 2. Same steps. Okay. So therefore, we can see that f in general is, we can even take 20 upon x square plus y square to the power 3 by 2 common, x I cap plus y j cap. This is how we can express the net force, because only internal conservative force is acting on it. There is no external force and there is no non-conservative force. Okay, so hope this is clear. Now coming to the second part of the question, coming to the numerical part of the question, we have to find the acceleration at the point 3 comma 4, and the mass of the given body or particle is 2 kgs. Okay, so from here we can see that at the position 3 comma 4, the force acting will be 20 upon, this will be 25 to the power 3 by 2 into 3 I cap plus 4 j cap. So this force will actually become 20 upon 125 into 3 I cap plus 4 j cap, or this will be the net force in newtons. Okay. So the acceleration will just become the net force divided by the mass and put the mass as 2 kg. Okay. So the acceleration will come out to be 2 by 25, 3 I cap plus 4 j cap. Or you can also write this as 0.24 I cap plus 0.32 j cap in meters per second square. Okay, so Kshitij, just check your answer once. You might have made some mistake with unit or something. Just clarify. Okay, Kshitij. But anyway, I hope your method was correct in general. Okay, now the second part, we are releasing the particle from the point on the x-axis 1,0, वहां से हम particle को release कर रहे हैं. So to understand the direction of motion, first of all, so the particle is released from here at 1,0 from rest. So to understand the direction of motion, we have to understand the direction of force. So force in general, we had just now seen, was this. Okay. So at any point on the x-axis, x comma 0, the force will simply become 20 by x square I cap. Just check it out. Put the value of y as 0 in this. So you can see that this will become 20 upon x square plus 0 to the power 3 by 2 into x I cap plus 0 j cap. So it will come out to be this. Okay. So that means there is a force along the x-axis of 20 acting when it is at x equal to 1. So by the time it reaches at x equal to 2, for example, the force would have been decreased to 20 by 2 square, but along the x-axis, so that's 20 by 4 or 5 newtons, and like that the force will keep decreasing, but it will keep acting. So at any general point x comma 0, the force acting on the particle will be 20 by x square. So the particle moves along the x-axis. So from x equal to 1, u equal to 0, okay, after a distance of 3 meters, at x equal to 4 meters, we want to calculate the speed of the particle. So we will use conservation of energy. Okay. So here to here, delta u plus delta ke should be 0. So if somewhere over here it is at 4 comma 0, you want to find out how much speed it has. So change in potential energy is potential energy at 4 minus potential energy at 1, and change in kinetic energy is half mv square minus 0, because it started from rest, so this should be 0. So potential energy at 4 comma 0 is 20 upon square root of 4 square plus 0 square. Potential energy at 1 comma 0 so you can see that half mv square is 20 minus 5 or 15 joules. Okay. So from that we can find out the speed. So again, this is one of those more tricky type of questions for JEE advanced level, and you will get used to this kind of application of work energy more in further chapters, but this will definitely make it easier to understand further chapters, those applications also. Okay. So with this, we conclude this extra theory portion for work energy, and next week we will start with some doubts from questions from your module and move on to heat and thermodynamics. Okay. So that's
Okay,
it for
sir.
today. Today's session, people. Yeah.
Bye, sir. Thank you,
All the
sir.
best. Bye. Wish you all the best.